Hello everyone. Today I'll be walking you through our project, a comprehensive evaluation of LLM-based collaborative filtering. Large language models offer a massive leap forward for recommendation systems because they can actually understand the semantic meaning behind movie titles and user histories. However, relying purely on off-the-shelf LLMs using zero-shot or in-context learning often yields poor results. For our approach, we were heavily inspired by a recent paper named Tolric, an effective and efficient tuning framework to align large language models with recommendation. The authors of Tolric identified that standard LLMs uh, often perform no better than random guessing on recommendation tasks due to massive gap between the language tasks they were pre-trained on and the specific recommendation objectives, which can be understood by the AAC score here given around zero point 0.5 for both cases in movie rec as well as book rec. And to bridge this gap, the Tolric implementation follows that large recommendation language model by formatting user interaction histories into strict instruction following prompts. To make this computationally feasible, they rely on a lightweight tuning approach called LoRa, which injects trainable rank decomposition matrices into the model while keeping the base parameters frozen. In this project, we explored four distinct approaches, uh, four distinct methodologies. Building upon these ideas, using MovieLens 100K dataset, we will look at zero-shot inference and isolated fine-tune tolerant implementation, and finally, our highly effective two-stage re-ranking architecture. Let's dive into the code. So, let's first look at how we handle the data. We use the MovieLens 100K dataset, and uh, to frame this as a binary classification task, we have converted it the ratings of all the movies given by users by changing anything greater than 3 is a liked interaction and 3 or below is a disliked interaction. For our evaluation protocol, we used a strict leave one out split. For each user, we held out their chronologically last liked movie as the ground truth test item. We then paired this positive item with 99 randomly sampled negative items. This creates a 100 item candidate pool per user, and our goal is to rank that true positive item as high as possible. So this approach follows a zero-shot inference, and running LLMs for recommendation is incredibly hardware intensive. So we loaded our models like Gamma 2B and Qwen 34B using 4-bit normalization, normalization or quantization. Uh, instead of having LLM, instead of having LLM generate text auto-regressively, we structure the input as an instruction following prompt. We feed the model up to 10 recently liked uh, and 5 recently disliked movies and ask, will the user enjoy this target movie? And the LM has to answer with a yes or no. And instead of generating the answer, we do a single forward pass and extract the raw logits specifically for the yes and no tokens. We then calculate our ranking scores using a binary softmax uh, to get to the yes or no approach. Here you can see the formula, and I can also show you some of the model as well. While zero-shot models are impressive, they lack specific recommendation alignment. So to fix this, we directly implemented the tolerate framework. The original paper proposes two tuning stages: alpaca tuning for general instruction following and rig tuning for recommendation specifically for recommendation data. Use the unslot library to efficiently apply LoRa uh, to the linear layers of the Qwen34B model. We formatted our user histories into strict task instructions and task outputs, just as the paper described. And here the model is initialized. Uh, and let me get to the bottom of this. This is our evaluation protocol. Uh, however, uh, our approach was tested on isolated subset of 50 users. This model actually underperformed on our zero-shot baseline. The model suffered from severe overfitting due to the tiny sample size, but this failure taught us a valuable lesson about scaling, uh, which leads us to perfectly into our final approach. Uh, and let me show you the result for this one as well. We actually got a hit rate and NDCG of 0.1000 at k equals 10, that is 10 users. And this was our supervised fine-tuning approach that was with Laura. Let me show you other things as well in this. Here are the training configurations, and we ran it for only one epoch because it was running very slow. Uh, and also, uh, it was running slow because we had too many examples for particular users. And these are some parameters we worked with. Uh, and this is the rank, this is the alpha, and we kept the dropout to a minimum of 0.05. And these are the target modules, all the LoRa parameters. And this was done on the Qwen 3 4B model. And this notebook is also working on the same model. And we have also worked on the Gamma 2 model. This also gave, this was also a zero shot sample as well. And this also performed similar to the Qwen model. And let me come to the results here, as you can see. And shall we get to the final approach? Yes. Okay. So running an LLM over thousands of items for every user is completely impractical, as we got to see in our last approach. So the solution is definitely a multi-stage architecture. In stage one, we use a uh, traditional collaborative filtering model, alternating least squares or ALS. So ALS is a blazing fast at matrix factorization. It quickly scans the entire catalog and retrieves our top 20 candidate set for each test user. In stage two, we bring a we bring the heavy artillery. We take our Qwen 3 model, fine-tuned via QLoRa, on a highly balanced dataset of 256 samples and deploy it on as a re-ranker to maximize speed. We use the VLLM engine by setting temperature to 0 and max tokens to 1. VLLM processes these prompts in massive batches, extracting those yes log probabilities to reorder the top 20 candidates. We retrieve this hybrid approach balances the computational efficiency of traditional retrieval with deep semantic mm, reasoning of large language models. So let me show you the result here as well. We have taken 256 samples here because in the previous approach we were taking thousands of examples and that was taking a lot of time. We used the Qwen 3 model as you can see, and these are the LoRa parameters, and this is the main SFT parameters. Here we went with sequence length 512. We can reduce it to 384 as well. Uh, it will make a difference. And we kept the purchase to one because it was taking a lot of time to train. And let me get to the final result as well here. This is our evaluation cell, and we have evaluated as per the instruction given to us. And here is the result. For our ALS pipeline, we got a hit rate of 0.6713, an NDCG of 0.4821, but we improved a lot on it by the LLM architecture we applied. So we reached 0.7031 in hit rate, and for NDCG we reached 0.5214. And to conclude our technical analysis, uh, I would like to finish with the report actually. This is our system architecture. If uh, you want to understand in a broad way, we first took the dataset, binderized it, splitted it, and then we built the prompt. The first we had tried a zero-shot inference approach, like we are directly giving the model to predict that. And this is the DORA approach, which we gave some samples first to learn from it, and then we came to the inference from the LLM, and then we did the ranking as well. But this was doing fine as well. Then this approach actually didn't work that well because of overfitting, and this approach was doing great for it. And this is our two-stage architecture. First is our ALS retrieval stage, and the second is LLM re-ranking stage. Uh, while we observe that the isolated fine-tuning on small datasets is prone to overfitting, combining Tolltech methodology with fast collaborating filtering baseline creates a viable two-stage path for practical deployment. Thank you for watching this demonstration. You can find, uh, thank you for this